All right, well, welcome back to part 2 of template metaprogramming with type traits. We'll resume where we left off last time. And I'm going to make sure get my questions. I forgot to do that. So we'll resume where we left off last time and talk about primary type categories. So there's 14 primary type categories, and they're on this screen. I'm not going to read them all. But all except null pointer were introduced in 2011. Null pointer was 2014. And these primary type traits all have to have a base characteristic of either true type or false type. That's fancy words just meaning they have to inherit from either true type or false type. All of them should yield the same result in light of CV qualifiers. We discussed that at the beginning of last session, but in case you're just coming to this one, the CV qualifiers are the const and volatile qualifiers that attach to a type. And so whenever you call is void or is integral with a type, if you call is integral with int, that statement is saying that you have to have the same result for int const, int volatile, and int const volatile. That the CV qualifiers should all return the same type for these traits. And for any given type T, exactly one of the primary type categories shall yield true type. Now, this has several implications. One, it means that if by chance you can't implement one of them, then you can implement it by just checking to see if it's not any of all the other 13. The other implications are that, remember I said you should not, the standard says that you can't provide your own specializations or you're going to get unframed behavior. And especially if you say, oh, I've got my own class and it acts like an integral or it acts like a pointer. So I'm going to say that it returns true for is pointer. Well, now it's going to return true for is class and is pointer, or true for is class and is integral. And you can bet that somebody somewhere, they're counting on the fact that the standard says that every type can only belong to one of these. And something is going to break at some point in time, and it's probably going to be when you least expect it. Don't do those kinds of things. So let's a reminder. We've already seen is void in the first section, and is void is the first one on our list. So let's just take a quick look at it. We have a explicit specialization for each of the 4 types here. We have the primary template. And I'll review this a little bit because we went over it a lot last time, but some people maybe do. The primary template, and then we have an explicit specialization for void const, for void volatile, and for void const volatile. So we've got an explicit specialization for all of those CV qualifiers. So now every one of them will return the same type, whether they have the void qualifier or not. So the next one is null pointer. Now, okay, this doesn't really look much different from is void. Why are we looking at this? Well, you're kind of right. It doesn't look much different. In fact, if you look at the red box around the top of is null pointer, that's our primary template. And then we have our specializations. And those specializations look very, very similar. Now, normally, my spidey sense would start tingling about now, saying we need something more since we're doing this twice. It's not that much code, but I'm starting to worry about this a little bit. So let's look at the next one, is floating point. We've got float, we've got double, we've got long double. And now this requires 12 specializations. This is starting to be a combinatorial explosion. So hold on to your pants here. All right, so there's our is floating point. If that doesn't scream to you that we need something better, then okay, well, maybe just wait. If this were regular programming, doing regular functions, we probably would have already refactored and abstracted things out to make it easier. But this is template metaprogramming. It's supposed to be painful. So we're just going to endure. Well, that's not really true. That's not how we should look at it. But I will say that these specializations like this are probably the fastest way of implementing it. Not typing speed, of course, but from the compiler's standpoint. when the compiler, in the compilation time, you'll notice as you start doing more of this programming that your compiler takes more and more and more time. And the compiler speed is going to be important. But if you're doing things like that require super high performance, you're very glad to trade those things off. But this doesn't look good. Okay, so it's painful. It doesn't look very good. What about isIntegral? There's 5 standard signed integer types: signed char, short, int, long, long, long. There's implementation defined extended signed integer types like GCC and Clang support 64-bit integers on some platforms. And there are corresponding but different unsigned integer types for each one of those. And there's all these char types. There's char and char8t, which is new in 20, char16, char32, and wchar. And then finally, there's bool. So this is going to require 16 times 4 specializations, because there's the without const, volatile, and const volatile. We're going to have to specialize that for every one of them. So thank goodness for Vim macros. So Vim macros to the rescue, and there's our code right there. All nice and neat, and let's move on. You know what? That just doesn't, I don't like this. We're begging for something else. We're begging for metafunction abstractions. Now, it shouldn't be that hard to understand the idea of metafunction abstractions, but because metafunctions might be new to most of us, that's what this kind of a beginner intermediate class, then maybe you don't really understand what that means too much. And I can relate. We've reached for this technique long time ago in regular or normal programming. My encouragement to you as you do more of these metaprogramming is treat it like regular programming. Because, well, that's really what it is. It is regular programming, especially nowadays and with all the type system. So we're going to look at how to take some metaprogramming abstractions. So leading to templates. Well, yeah. Okay. So step back to the land of regular functions. All right. So we've been talking about doing metafunction abstractions. We're talking about regular functions. So we're going to step back again and reseat ourselves. Pretend that we need to implement these same ideas with strings instead of types. We're going to implement this in a very similar way. There you go. There's this void. Compare the string against every one of the possibilities. And there's his no pointer. Compare the string against every one of the possibilities. And there's his floating point. Compare the string against every one of the possibilities. So that's what you did, and you wrote it. I mean, you've got tests, and you submit this for code review. So you submit this code for your code review, and your code review comments start coming in. And so probably not too many people are happy with that code. And while we remember that specialization is going to have our best issues, that's probably not going to be the case in this code. And if that code would not pass muster in doing regular code, then those techniques are probably not going to pass muster in metaprogramming. Now, we have to use different techniques to figure out what we're going to do, but we still should apply the same rules of what is good and what is not. So let's get rid of this. So let's take a step in the right direction. We're not going to try and solve the world's problems or get the ultimate solution here, but we're going to take a step. So in this case, we've got our functions, and let's say we had a function called remove CV that went in our string and removed all those const volatile things, so that all we had was just the void. Then we could easily write is void, right? We could easily write, there's our is void. Is void is just remove if the remove CV is equal to void. Same thing with null pointer. Remove all the const volatile stuff out of there. And is that what I have left? Yeah, then it is. And the same thing with float. Remove it, look and see if it's a float, a double, or if it's a long double. That's a step in the right direction. And even with isIntegral, we can have another one that says strip signed, that will kind of remove the sign. It knows how to remove the signed or the unsigned and try to figure out what the underlying thing is. And then we could have a function similar to this. Now, this is better than having all those explicit string comparisons. And so in the same way, it's probably better that we do something similar instead of doing all of those explicit template instantiations or specializations. So we talked about remove CV with strings, let's talk about remove CV with a metafunction. Now, we already have remove const. And remove CV, by the way, the CV are the const volatile qualifiers. So that's const and volatile. So we already have remove const. So what we need is a remove volatile. And then we can compose them together to get remove CV. And composition of metafunctions is similar in thought to composition of regular functions. It's different in implementation, but it's similar in the idea of what we're trying to accomplish. So let's look at remove volatile. There's our formal definition. Basically, it says any top-level volatile qualifier, get them out of there. And there's our implementation for remove volatile. It's eerily similar to our implementation of remove const. In fact, just replace const with volatile. So there's our primary template. It does nothing. So if there's no volatile in there, it's just going to return the type that you give it. Here's our partial specialization. Now, in our partial specialization, if volatile is part of the type, then we're going to pull the volatile piece out, and all the pieces of the type that are left, we're going to use those as the green piece that goes into the T. And we're going to inherit from type identity, which, if you remember, exposes a public type named type, which will be T. And so we will have removed our volatile just like we have removed our const. So remove CV. The formal definition says that it's going to remove any top-level CV qualifier. So basically, it's going to remove const and volatile. And so in this case, what we're going to do is remove volatile and then const. Now, there was a question earlier in session 1 asking if alias templates could be considered metafunctions, because I said metafunctions were classes. Well, yeah, so this is an alias template, but this is a metafunction. So let's look at it in a little more detail. It doesn't look like a metafunction, this remove CV. It doesn't look like a metafunction that we've had before because it's not a class. But it's basically saying that remove CV is going to be the same thing as remove const and then remove volatile, okay? So this is what we've got. Remove const with that right there. The remove volatile underscore T, remember, that's a convenience for calling remove volatile. It's the same thing as type name, remove volatile, and asking for the type. And so what we're going to do is we are going to compose this. We're going to call remove volatile to remove the volatile piece off the type, off the type. And then the result of that, we're going to feed into remove const. Now, there's something interesting here. Remove CV takes remove const, but it doesn't do remove const underscore T. It does remove volatile underscore T, but it doesn't remove const underscore T, because remove CV is going to be a meta function. We want to be able to call it like a function. If we had said that remove CV equals remove const underscore T, then it would have invoked the remove const meta function. And that's not what we want. We're defining remove CV as a meta function, and it's actually going to be the exact same as the meta function remove const. Okay. So let's look at an example. Remove CV of int const volatile. There's the type. It's going to be the same thing as remove const of remove volatile T, int const volatile. There's our type, which is going to be the same as remove const of type name, remove volatile, int const volatile type, which is then going to be the same as remove const of int const. So what we've done is we've given it int const volatile. That has gone into the remove volatile meta function and it's been invoked, because we see the underscore T means invoke the remove volatile meta function. Get its type and return it. So it stripped off the volatile part and returned int const. And then that got pulled back, and so now we have remove CV is equal to remove const int const. But why? I thought we were going to remove the const. Why is the const still there? Well, remember, this is a meta function. So once we call type on it, then we're going to get the int part out. Okay? So let's look at remove CVT. This is invoking remove CV. There's our type name with our type that comes down, and we do the type name dance. It's hidden because it's up in there when we invoke it. And then now we end up with our int because we're going to call : type on the type that's wrapped. So when you use a type alias, an alias template as a metafunction, it is a metafunction. Don't confuse it with calling a metafunction, because what you're doing is you're creating another metafunction that is equivalent to the metafunction that you're making it an alias for. Okay, so, earlier I said specialization is like comparison for functions of types, right? But it can be verbose. And it can be used in a context that allows explicit specializations of templates. So that's the only place you can use those specializations, the explicit specialization. And so let's write a comparison for metafunctions for types. And we're going to call it isSame. And the reason we're going to call it isSame is because that's what the standard library calls it, because this is a type trait from the standard library. And so we have our primary template, and it takes two types, any types. Now, remember, I think earlier we had only worked with one type on here, but we've got two types. It takes two of any types. That's why we've got type name T1 and type name T2. They could map to anything. They could be the same type, but they don't have to be. So, since our special case is the same, right? We've got, you see how the stuff in the green box, it's the two T's, but look above it, you only see one T in the angle brackets. So remember we talked about partial specializations. An explicit specialization means the angle brackets are empty. A partial specialization is that there's something in here and we're gonna specialize it in a way. Now, it might be confusing that there's only one type in this angle bracket up top, and there's two types here. But that's okay, because you have to think of this upper part as almost like the parameters to a function. It's not the same. And this is a little interesting, because in this case, if you remember, I said that anything inside of these angle brackets, if they're empty, we've got a full or explicit specialization. We've got something in here, so it's partial. But there's only one of these parameters, but I need two in my specialization. And that's okay, because I don't want you to be confused by what's in this set or not. Think of this, it's not quite right, but it's close enough. Think of this almost like the parameters you pass into a function or something. You've got a bunch of them. It's not that. It's not even really that, but you can have as many of those as you want, right? You can have, when you have a specialization, you can have as many things in here as you want. This has to match that. Okay, so when you specialize it, this has to match this. But it doesn't matter what's in this part. Anything you want to put in there is fine. Okay, and so in this case, I've got one type because I want to match when they're both the same. Okay, when both of those types are the same. So, this specialization, think of it as it's like says, hey, I got a type T. Now, that T can be anything. And when the template is instantiated in such a way where both types are that anything, that T, then choose this specialization, right? So isSame can be instantiated with any two types at all. But anytime it gets instantiated and it matches where they're both the same, then this one's gonna get done, right? So the first one's gonna get matched, right? So let's look at, there's only two of them here, so it's not a combinatorial explosion here. Let's look at the first one. If I pass it in a couple of types, it's going to get matched. No matter what two types I have, the primary template is gonna get matched. That one will get matched every time, no matter what two types I put in. But the second one will only get matched whenever the types that you put in are the same. That's why there's only one type up top. Because if that type can describe the types that are inside of the specialization, then that one gets matched as well. And the rules say that even though both of them get matched, it's going to select the one that is the best specialization, the best match. And so the best match is going to be this one, which is going to be true whenever the two things are the same. So let's look at this in a little detail here. So if we call is same int and unsigned, then T1 is going to be int and T2 is going to be unsigned. So the primary template is going to match. The primary template matches with T1 matching to int and T2 matching to unsigned. But there's no way to make the second specialization match. I mean, how can you pass it int and unsigned and make both of them be equal to the T? I mean, you can't because they're different. They both can't be equal to the T. So that one's not going to match. But if we look at the second example where we send in two ints, the first, the primary template, it's going to match with T1 equal int and T2 equaling int. And then the second specialization, it's also going to match because it can create is same int with the T equaling int because it's only, there's one. It can only be one. And if they're both the same, then it's going to match. Okay, I hope that's a little more clear. Sometimes these specializations are a little bit tricky. And we've got a few more because there's just subtle examples, subtle differences. So let's just assume that we have this thing I call is same raw. Now, to be sure, this is not a standard type trait, but it's kind of useful. And what it really does is it takes two types, removes their CV qualifiers, and then compares them, right? It just says, hey, remove the CV qualifiers, and if they're the same after removing the CV qualifiers, then I'm going to treat them the same. So this might be helpful considering that all of our type traits want us to remove both the const and the volatile qualifiers. So let's go back to is floating point. So again, we use an alias template. Is floating point is an alias template. It's not a class. And it's basically going to resolve strictly to bool constant. And we're going to call our is same raw. If removing the const, the CV qualifier from both sides yields the same thing, then we're a floating point. I hope that makes sense. That's very close to the string example we were looking at from regular programming. I see a question. I'll get to it in a second. So we have this bool constant of integral const, and that's really what those guys resolve to. That's what is floating point is. It's a bool constant, which is a constant, an integral constant. So let's look at is integral. Is integral is very similar. It's just a little bit longer. Now, I didn't implement the part about the unsigned because really make unsigned and make signed actually have a little bit of complexity to them because depending on what it is, you have to find the type that has the right size, and it's probably a little bit more involved than an example here. But you get the idea. This is better than the 64 specializations we had. It's still not great, and hopefully we'll get time to see something that is better. But this still is way, way better than what we had before. And you can see the power of doing these abstractions. And it's really not that bad once you get used to it. You create your little function, your meta functions, just like you would create little functions when you were writing bigger code. You don't put everything in one big function, at least not anymore. And so we can happily go along and write these smaller meta functions to help us. Now, we could implement, if we had a thing called is type in pack, and we might get time to me showing you how to implement that. But imagine there was a meta function called is type in pack, and it took a type and it took a list of a bunch of other types. And it basically returned true if that type was anywhere in that list. Then you could imagine that something like this is integral, is type in pack, give it the type, and then give it the list of types. And it would go off on its happy way and check to see if it was any of those. Okay, so let's get to this question. Intuitively, I understand what is the best match when more than one template definitions match. How is it formally defined, though? That's a great question, and I'm not big on standard ease. So to get the actual formal definition, you're going to have to go to the standard. But basically, for template specialization, it's just as intuitively as you would think it is. It's the best match. Think of it like this. If you took all of this isn't exactly how it works, but think of it this way. Take all the types in the world. You've got each one of the specializations, or each one of the matches is a bin. Throw all the types in. The one that is the most specialized is the one that you're going to pick, right? Because I'm matching against the general one, but there's only one over here, and it's the one that matches me exactly. It matches most of my stuff. I might match with, if I'm looking for something with const in it, it might match with something with an int and a const and some other values. But you're looking for the one that is the most refined. And I don't know what the language is from the standard because I just don't remember it. I read the 98 standard from cover to cover, and I will never do that again. I probably don't have the stamina to do it anymore, but I don't remember. But it's basically what you would think from an intuitive perspective, is that the match that is the closest to your type is what's going to be matched. And there is a sophisticated algorithm, and it's very well described. I'm just can't really describe it very well aside from that. It is the best match. I mean, look at all the examples, and you can clearly see the best match. I apologize for not being able to do better on that. So let's look at isArray. And we look at this one because it's still partial specialization, but it's different. It uses, hang on, I had more questions popped up there. Let me see if I can do those before I get on here. Would this match something like a size T or a unit, or would that need to be explicit? Oh, good question. Good question. No, you will get a size type promotion for the integers if you have things. So like right here on this one, it's got a type T and a size Tn. You don't have to cast it to a size Tn. You could throw in a 10 or something, and it will promote it to meet that. If I had a primary template type name 1, type name 2, type name 3, struct is same. Can I write a specialization template type name X, type name Y, struct is same X, Y? No, you couldn't. Because you've got because your is same there takes 3 template parameters. And if it takes 3, then the specialization has to have 3. So let me see if I can show you on here. isArray, the primary template, isArray has 1 parameter. Therefore, every specialization must have 1. If the primary template has 2, then every specialization must have 2. You have to have the same number in when you specialize it. The number in here, when you're declaring what your variables are for your partial specialization, you can have as many as you want there. But in this, it has to match exactly in what you have in the primary template. Okay, I think I'm caught up on questions, which is good. Because it's a tutorial, so I should be processing questions. All right, so on isArray, when we look here, it's interesting because we have a type and a non-type template parameter. We have both of them. And this is just in the specialization, right? So I'm trying to match a type, but arrays, there's 2 kinds of arrays. There's arrays that are bounded with a size. And that's what this would be. It would be matching an array. Think of it like int angle bracket 5, right? I've got an integer of 5. I've got an array of 5 integers. And so this is going to match with a type of an integer with 5 elements in it. It's going to match the int with the t and the 5 with the n. And yes, if you just give it a 5, which is technically an integer, it will match to the size t. The second specialization is for an unbounded array, and which has no size. So its type doesn't have a size. So this one's just going to match any unbounded array. And so it doesn't matter what the type is, just any array at all. And these arrays can have arrays within them, right? T itself could be a list of arrays. That's okay. This is just any array. So in this case, no wonder int5 was on my mind because that's what I wrote. So we've got here that int5, the primary template is going to match with t because int5 is a type. Any type's going to match with the primary template. The first specialization is going to match because it's going to match with the int and it's going to match with the n equals 5. But there's no way to match with the second specialization. So the first specialization will be selected because it is more specialized. Now, there are cases where the compiler can't figure out which one's more specialized. And in that case, it would be ambiguous and you would get a compiler error. And so here's our second case where we have an array that's unbounded. Of course, the primary template is going to match because it takes any type. And the second one is not going to match because there's no way to put T and N together in order to get a valid type. I mean, you just can't. There's no way to form that together in order to get a valid type because int square bracket has no n, it has no integer. So there's no way to create that one. And the second one will match with T being int. Is it fair to assume that there is the possibility of ambiguities which would result in compile time error message? Yes, most definitely. When you create your specializations, you need to make sure that you're creating them in an unambiguous manner. And if you do have ambiguous specializations, the compiler will yell at you. So it's not like you'll get in a case where you've got some bug because the wrong thing. No, the compiler will figure out what those ambiguities are. And it'll be pretty clear to you once you look at it in most cases. Okay, so is pointer. It's pretty simple. Why are we even doing this one, right? I mean, it's a pointer. The primary template says, hey, false type. In general, things aren't pointers. So the primary template is false. The specialization, I take a T, and this is a partial specialization for any pointer. A pointer to anything. I don't care what it is, and I'm going to return true. But that's not all there is, because we have to take into account this little CV thing. And the little CV thing is going to bite us in the tush on this. So we have to basically take our implementation of this pointer and put it into a detail and put it somewhere. We have to do some implementation. This is not the only way to do it, but we have to account for the CV qualifiers. And so in this case, the way we're going to account for the CV qualifiers is that we're going to put this implementation into this detail namespace, and we're going to have isPointer. Now, remember, it is an alias template that resolves to isPointerImpl with remove CVT. So I'm calling our remove CV meta function to remove all the const volatile qualifiers off of this type. And then I'm going to pass it into the isPointer. Because what if you had a const pointer to T? Then you want to make sure that those get resolved. So we're gonna handle that situation. But otherwise, it's pretty similar to what we've been doing before. Okay, this is the one we were talking about right before the break when somebody had asked, are there cases where the compiler doesn't support them? So isUnion, this is an example of one of the meta functions that it's impossible to implement without compiler support. And the reason I include this is I want to explicitly point out that some information about types, while available to the compiler, they're not available with the construct of the language itself. Remember, metaprogramming in C++ is not a first-order language feature, at least not yet. And while a lot of that stuff is changing, there's still a lot of idiomatic conventions, and some things you just can't be done without compiler support. And so this is what compiler support kind of looks like. That under Union, right? You know how they keep talking about those reserved words that they're allowed to use? Anyway. Okay. So this one is going to be kind of fun. Is class. Now, why am I going to do this? I mean, usually it's almost always implemented as a compiler intrinsic. In fact, most of the type traits nowadays are implemented as compiler intrinsics because the compiler is much faster dealing with intrinsics than dealing with even the simplest template stuff. So And without the compiler assistance, it's kind of impossible to distinguish between union and non-union class types. But we already have is-union. I mean, we just saw is-union. We got help from the compiler to implement that one. And there's some interesting things that we can learn in implementing is-class. Remember, I'm not trying to show you how to replace the standard library. You should use the standard library. You should use the type traits in the standard library. What I'm trying to show you is trying to help you understand what they're doing so you can write your own, but also so you can more confidently use them on your own in your programming. So if we could tell the difference between a union or a class, or if we could tell, at least be able to group them into a category, right? There's these 14 different unique types. And if we could separate the ones that are either union or class, I know without help from the compiler, I can't tell the difference between a union or class, but maybe I can at least group those two off from the rest of the herd. And each type must be in exactly one of 14 categories, right? So each one of them has to be in each type has to be in exactly one. So I know that if the type is either a union or a class, then I can say, oh, discount the ones that are union, because I already have that meta function. So let's try and learn some things. And this is where we get into the kind of the deeper end of the pool. We've kind of been in the shallow end. We're just going to cross over. We're crossing over like the little line, and you might step over your head a little bit, but there's a lifeguard on duty somewhere, and they'll throw you a little unicorn ring. So what do we know about unions and classes that's unique to just those types? Well, they can have members. Nothing else can have members, right? A class, well, a struct, but a struct is considered a class. Classes and unions, they're the only ones that can have members. So if we could devise a way to detect if a type can have a member, then we're golden. So how can you tell if a class has a member? Well, if it has a member, it can have a pointer to a member. And the syntax for a pointer to member is valid for any class, even without members. So as long as you just have a struct, you can create a type that represents a pointer to one of its members. A question, does is-union consider std variant as a union? No. And the reason is because every type belongs to exactly one of the primary type categories. And std variant belongs to class. Std variant does not belong to union. Just like is function does not include std function, and is pointer does not include smart pointer. It doesn't include shared pointer and all that stuff. That's a good question. So if we can devise a way, then what we want to do is figure out this pointer to member syntax, right? If I can create a type for it. So int star is a valid pointer type. It doesn't have anything to point to, but it doesn't matter. It doesn't matter if it's pointing to anything or not. It's a valid type. And remember, we're dealing in the type system. It doesn't matter if it has something to point to. What matters is, can we represent that it could possibly point to something? So if we have a class foo, then int foo : star is a member pointer type. It's pointing to a member of type int. Doesn't matter if foo has an actual member of type int or not. We can still construct the type of pointer to it. So we have an empty struct. It has no members of any kind. An empty struct bar with no members of any kind. I can still create a pointer to it, right? I can create a type that's a pointer to it. But I can't create this one. This one's going to generate a hard compiler error because you can't create a member pointer to a long. That doesn't make any sense. It can't have members. So if we can figure out how to do that, then we're golden. And what we're going to do is we're going to learn about the thing that you've all been waiting for, but nobody's really said it. I'm going to say it in a minute. So before we get to it, though, I want to talk about something called function overload resolution. And to do that, we're going to re-implement is null pointer in a different way, completely different way. All right, we're going to re-implement is null pointer. And we're going to say that is null pointer is the result of calling this function. So decal type says, compiler, pretend that you're actually calling this function. Give me the type that you would have returned if you call it, but don't call it. I mean, note that those two functions up there aren't even implemented. So decal type just says, compiler, pretend you're going to call these functions. If you called them, what type would you return? And this decal val, it basically takes T and converts it to a reference type. Now, it can only be used in unevaluated contexts like this one. And so this alias asks the compiler to pretend that it was making an instance of a type and passing it into those functions. And it was asking if it was null putter. And what type would it return? Now, if we look at here and we see is null pointer of int, we should be able to see clearly that is null pointer of int, it can't call the int of int, it can't call this one. Because you can't convert an int into a null putter. You can't do it. So the only one it can call is the purple one, right? And it should be quite clear that this one can only call that one. Will call that one. Now, it can call this one as well. It can call the one with the ellipsis. So in this case, what happens is that both functions are valid. Remember earlier, we were talking about template specializations, where two specializations were both valid, and then the compiler picked the best one. Well, this is similar. But it's overload resolution for functions rather than for those template classes. And so it basically goes in and it says, hey, which one has the best match? Which one of these functions am I going to call? And it picks it. And the ... will match anything. It'll match any number of anythings, but it's always the worst priority. It will only ever be used if nothing else matches. It'll only ever be used if it's the only one that matches. And in this case, both of them match, so null putter gets called. The overload resolution is important to understand when you start dealing with advanced metaprogramming techniques. It actually is important to understand no matter what you're doing in C++, because it comes up in a lot of things, not just in this. So let's look at one that another type that we've seen before, isConst. Now, this time isConst, we implement it in a little different way, and we use a technique called tag dispatch. Now, tag dispatch is where we're creating a type that's just being used as a tag, and we're going to use type identity, because type identity is a type. You can instantiate it, and you can pass it around, and it takes no space. It's very efficient to pass these guys around. Now, I don't recommend or encourage this version of isConst. I'm showing it to you to demonstrate how this technique is used. So there's our decal val again. I'm creating an instance of type identity T. Okay? I'm going to pretend that I'm constructing an instance of type identity T. So that's going to return to me a reference to type identity T. And then the decal type is going to mean I'm going to pretend to call isConst with it. And one of those two functions is going to be called. Now, in the first case, I get a match. It's null putter. It doesn't have a const anywhere in it. So that's the only one that matches. And so that's the one that's calls. And so we get false. On the second one, however, both of them will match. But this one will be a better match. And so that's the one that will get called. Now, here's the big word, the SFINAE word. Now, that word, the acronym, came about in this book by David van der Voorde. I know I mastered his name, but I bought his book, and I bought every book that he and Nikolai have written, so forgive me for masking your name. This SFINAE stands for substitution failure is not an error. And what it means is that under certain contexts, when the compiler is binding an expression to a template parameter, then an error that normally would have generated a compiler error doesn't generate the error. It just forgets about it and moves on, right? It's a Jedi trick. You know, this is not the error you're looking. It's just that go away. but it's a specific context. It's not every context, but it's a very specific context. So in our previous examples, both functions were valid. Both functions compiled, and the compiler picked the one that best matched. But what if we want to match something that may not be a valid C++ construct? I mean, like, say, a pointer to a member, since that's what we're trying to figure out, we're trying to deduce. You can't just pass anything to a pointer to member because you're going to get a compiler error. So let's walk through what happens in a couple of examples. Here, we're explicitly providing a foo into can have pointer to member, right? And when we do that, we get both of these functions. The compiler is going to spit out both of these, okay? It's going to spit out can have pointer to member foo int bar star, and it's going to spit out can have pointer to member foo ... Both of them are going to be valid. And the compiler will pick the one that's the better match, which is going to be the one with the member pointer, the pointer to member. Now, if we look at it with another one, instead of because the last time we passed it foo, right? Foo, which was a class. This time we're going to pass it int, which is an integer. It's not a class. And so what happens is the compiler is still going to try and spit out both of these, right? It's going to say, hey, I'm going to try and instantiate both of those function templates. But the one when I try to instantiate it with the one that I try to instantiate with an int, that right there, that ain't C++. It's going to barf on that. It's not going to compile that. And so we're going to get a compiler error. That's not quite what we want. We don't want a compiler error. But you remember what I said about the reason when substitution failure is not an error. It's when you are substituting for a template parameter. So let's create an extra level of indirection and create our template parameter. Specifically, we're going to create this one right here. And we're going to call can have pointer to member with a deduced type, with T, a dependent type. Now, down here, we're still going to call this with int, right? I haven't changed this at all. I'm still calling this with int. But instead, I'm going to call this template alias, right? We're doing abstraction stuff. We can create one of these. I'm going to call that guy, okay? And by calling that guy, I'm going to have a deduced context, okay? So I'm going to have a context where SFINAE can come in, okay? So let me try to recount this again. The template parameter that we've added, let me go back and put this up. This template parameter, this alias template that we have added, that this guy calls, means that when this int gets substituted for that T, now we've got a substitution occurring. I'm saying instantiate this template and force it to have an int into this T. Well, in the previous slide, this context, when we were called it in the previous context, we tried to call this thing directly from here. It wouldn't let us. It gave us an error. And that's because we were directly shoving the int in. But in this case, right here, we're substituting it for a template parameter. That's why it's called substitution. Failure is not an error. So the error isn't that this doesn't compile. The error is that when you substitute an int for T, when you try to plug an int in for this T, this doesn't compile. So the substitution fails. And when the substitution fails, then it means that that's not going to be valid. So when we try to call this, with this guy, and we pass it an int, we're going to still get the same compiler error we got before, but the compiler is going to swallow it because it says, hey, I got this, this doesn't make any sense to me. I can't compile this. But it occurred as a direct result of me trying to substitute a type for a template parameter. And because of that, it's not an error, and I'm going to go away. Now, there we go. He says, these are not the errors you're looking for. Move along. Now, with this in hand, we can try to implement isClass. It's very simple, actually, but we need to understand the ideas behind SFINAE. And trying to get to SFINAE, there's a lot of ways of implementing this isClass, but one of the reasons I did it like this is because I wanted to introduce you to overload set resolution. I wanted to introduce you to those concepts and SFINAE, particularly in that context, because that's where it originated. And now we can use it in lots and lots of different ways. But in this case, if we look at this isClass, we can see a number of things. Here we have isClass that is basically saying, all right, isClass is a metafunction. This don't look like any metafunction we've been looking at, right? This doesn't look like a class, but it's gonna say, compiler, pretend that you call isClass or union, passing it the T with the null putter, which is then going to invoke this, isClass or union, or this one, right? Depending on the match, right? And it's going to say, one of them, if I pass in a foo for this, if I pass in a foo, both this one and this one will be active. And this one will be selected because it's the better match. And so it will return true that it is a class or a union. But if I plug an int in here, if I call it with an int, then this one will be valid. This one will not. This one will generate a compiler error. But because it generates the compiler error, as a result of substituting for this template parameter, that error goes away. So this function doesn't even exist, and only this one exists. So now we have a way of turning a compiler error into false. I think that's kind of cool. Even now, after having seen this for 20 years, I think this is kind of cool. So we could also implement isClass with context per functions. Right? Here's a context per function that returns an actual bool. They do the same thing. They do the same SFINAE trick, right? They do the exact same SFINAE trick. The only difference is this one is a bool constant, doesn't use decal type. It's a bool constant that calls this context per function that returns a bool. And it just fills in the bool for that bool constant. Just an alternative way of handling it. There's tons and tons and tons of ways of doing that. So if I have a lot of questions, I'll do those. If not, I might try to show you the is in pack, though I don't want to run over, even though I lost my connection. Is declval needed in slide 79? Doesn't type identity have a default constructor? Is declval needed in 79? Is declval? Oh, doesn't need it. Oh, you know what? It doesn't matter whether it has a default constructor or not. Yes, you could use it that way, but yes. So let me go back and show what the question is asking in slide 79. Which figure out make sure I'm looking at the one you're looking at. Okay, in 79. Yes. So this declval. Yeah, technically, you don't necessarily have to have it because you could say type identity T and then put the little squiggles and it has a constructor and it'll do it. However, the concept with declval is that it's in a totally unevaluated context. And so my personal, when declval first came out and I started playing with it, I struggled between what I should do or what I shouldn't. After having several bugs that cost me a lot of time to track down, my own personal convention is that if I'm using something in an unevaluated context, I'm going to use it like that. The only place I won't use declval is in places like in the auto reduce return type, right? When you specify the return type after it and you say decal type there, because you have access to the actual variables that are the parameters that come in through the function. But other than that, I always use declval, even though you can get away without it. Let me see if I can run through this real quick. At least put it on. And so remember we had this thing called. I don't see any. Oh wait, nope. Maybe I should answer these other questions. That's what I'll do. Is there a way to find out if a class has a specific method? Yes, there is. There's the old way of querying it, and there's kind of a new way of doing detect. There's lookup the is detected mechanism. There, you could use stood void t for it. You could use is detected. You could, depending on the context, if you're trying to use it on a function, you could just use the decal type. You put an arrow, right? The trailing return type, and use decal type, and then your context in there, and that'll give you SFINAE results as to whether it's actually active or not. There's lots of ways of doing that. Can you spend some more time explaining the decal-val decal type pattern? Okay, so decal type tells you to pretend that. Let me go back to one that has both decal type and decal-val, which I think was 79. Is that the one? I have to get where I'm seeing something different. All right. Okay, there we go, 79. Okay, so the decal type. Decal type basically, see how this parenthesis is right there? That parenthesis goes all the way to here. So everything inside of decal type, it says, all right, compiler, pretend like you're making this call. Evaluate this expression. Doesn't have to be a function call. Evaluate this expression and give me the result, the type that you would get from evaluating that expression. That's all. That's what decal type does. Pretend like you called this and give me the type as if you really called this, what would you give me? But we're in an unevaluated context. We can't really make this function call. And so in an unevaluated context, decal-val is there so that you can grab a reference to any type. And the question earlier about since type identity T didn't have a default constructor, one of the benefits of decal-val is it doesn't have to have any constructors at all. It just gives you a reference to something as if you had created one, as if you had one. But this is an unevaluated context. And so decal-val can be called in an unevaluated context. It's just a declaration. There's no implementation. It's illegal to try and implement it. To try and instantiate it. It's illegal to try and have one. So this decal-val says the stuff inside of these angle brackets, I want you to pretend that you've created one of those and return a reference. That's really all it does. Decal-val's implementation is add a reference to whatever you get here. If what you have is a value, then you're going to have an R value reference. Like here, this will return an R value reference to T, right? This will basically return, this std decal-val right there will basically return type identity T ref, okay? That's all it's doing. It's returning a reference so that it could be used and passed to this isConst. Is there a way the slides can be made available for reference? That's a good question. I imagine that they have I imagine that there's probably put them in the GitHub or something, and so I'll make them available. I don't know what I can do to try and make all the little graphic-y things in there, but I don't know if they'll. I don't know about that, but I'm sure CppCon will have them available in some way. I'm out of time. I apologize for losing my connection earlier. I really, really am sorry. I know I had way much more material than I was going to cover because I wanted to make sure I answered any questions that you had. I will be around. Find me if you have any more questions, and if there's enough interest in more questions, maybe we'll do one of these AMA things so you can ask specific questions about this type of stuff. I don't know. I want to get asked about anything, but okay. Thank you.